rational root theorem, I do want to clear up just one other idea that occurs in graphing polynomials and kind of review our factoring from the previous section 4.4. So first of all, on this slide, I have a statement up at the top that says finding zeros is equal to finding what? X-intercepts. Awesome. Now, the x-intercepts will only show up if the zero is real, right? If it's imaginary zero, it's not going to show up on our graph. Okay. We have to talk about something called multiplicity. Okay. And multiplicity is basically how many times a zero is a repeated solution or factor. And this SOL apostrophe N, that's my abbreviation for solution. So I'm too lazy to write it out. If you don't like it, you write out the word solution. So it's how many times a zero is a repeated solution. If it's a repeated solution, it would show up as a repeated factor. Okay? So it would be the same thing. So I have an image that we can kind of go off of, and it's not going to tell us everything we need to know about the polynomial, but it tells us a little bit about the polynomial and multiplicity. I'm going to trace on the curve because it's a little bit hard for you guys to see. If you want to make the polynomial kind of like mine in your notes, I have a 0 at -2, at 0, and at 1. So if you kind of want to sketch the same shape, it doesn't have to be perfect. My polynomial looks something like this. Okay, so we've talked about previously, early in the chapter in section 4.1, like, just looking at a graph of a polynomial, like I know what its end behaviors are doing, right? On the right and the left, my y's are approaching what value?
Positive.
Positive infinity. My arms are straight up in the air, right? Reaching towards positive infinity on both sides. Okay? So I know some things about the equation of the polynomial. Like I know it has a positive leading coefficient because the right side rises. And I know it has an even degree because the left side also rises. That's the same thing. We would also be able to say like what our constant value is because of our y-intercept. In this case, our constant is 0. And if you think about in context of section 4.4, there was that question on that factoring homework assignment. I want to say maybe it was 72. Where it's like, how do you see it when you look at the graph? What's the factored form from the graph? We also know what some of the factors of this graph are, right? Since the zeros are at -2, 0, and 1, what are some of our factors? Well, those are our zeros. What do the factors look like?
I think it'd be 2, 0, -1.
Okay, in factored form, we must have had an x plus 2. Because if you set x plus 2 equal to 0 and then solve for x, doesn't it come out to be x equals -2? And then if you have a 0, that's usually just x. You can write x plus 0 or x minus 0, but I don't. Okay. And then because you had 1 as a solution, you must have had a factor of x minus 1. But if you multiply 3 factors together, what would be your degree? It would be cubed. At most, I'm going to get x cubed when I multiply all 3 together. And we had said previously, because both arms were up in the air, that it had to be even degree, right? So something's missing because I have an odd degree, cubic polynomial. I only have 3 factors. So this is going to lead us back to this idea of multiplicity. It is possible for your factors to repeat themselves. So I'm going to tell you this. One of those factors is repeated, and you can tell it's repeated when you look at the graph. it looks different than the other zeros.
Is it 0? Oh.
Well, who wants to argue for what they think? Why do you think -2 looks different, Logan?
Because earlier when you said that we had an imaginary solution, it doesn't necessarily turn, it just turns like it has shape, and we have that, except it crosses at -2, which means either there's an imaginary solution there, or it repeated itself.
Okay, so something maybe happened at -2 because you see how it kind of like bends right there? Okay. But a lot of people said 0. Why did you say 0?
Can I kind of say like what I think?
Yeah.
Compared to like the turns right there, compared to the two last 2 points on the graph where they just continuously going up, compared to 0 where there's 2 turns.
I think you guys both make great arguments. The one that's like really super different is 0. Okay. Now, I would agree with you, Logan. I think something strange is happening at -2. And I'm glad that you saw that. I think there are repeated solutions there, but it's different than what I'm going to talk about for multiplicity. So I'm going to get there. Okay. But let's all say, I mean, I would guess most people eyeballed this and thought, that's strange at 0 because the graph touches the axis, but really we could say it turns around. Or some people describe that, we've said before, as like a bounce on the axis, like some of our quadratics bounced on the axis, like turned around on the axis. Okay, so that's a special case. If you have a turn or a bounce, you have even multiplicity. Okay. So in your notes, you need to have something about even multiplicity and odd multiplicity. And you can put this into your own words, okay? Even multiplicity, if a graph or if a 0 appears an even number of times, the graph turns on the x-axis. So we're really going to need to keep our eyes open for that. Okay, that it turns on the x-axis. Okay. If it has odd multiplicity, the graph crosses the axis. Not if the zeros are odd, if the number of times they show up. Okay? Because multiplicity is how many times the 0 is a repeated solution, not what the value of the 0 is. So we just said 0 has to have even multiplicity, right? So that means that this factor of x had to occur an even number of times. So maybe there's an x squared out there. Do you agree that's a factor of x times x? And then that means that it repeats an even number of times. That's what I'm referring to as even. That it repeats twice, and that's even. Now, for Logan's issue that he saw, okay, this sort of like strange curve thing right there, that could be like the result of an imaginary. Or it could be an odd multiplicity more than 1. So this is -2, x plus 2, instead of being like a degree of 2, which is an even multiplicity, maybe it occurred 3 times. Okay, so I could have x plus 2 cubed. If you had x plus 2 cubed, if -2 appeared 3 times as a 0, it would still cross the axis, but it would probably do something strange like what Logan is seeing. And that would mean in factored form that I would add 2 more x plus 2's, right? Now let me ask you this question. If I multiplied that all out, what would my degree be? x to the 6th. I'd have x squared. When I multiply this all out, I'm going to have an x cubed at the front. And then when this is an x to the 1st, so if I just add up all my exponents, I would have x to the 6th. It would be a 6th-degree polynomial. Could that still fit my n behaviors? Rise, rise? Yeah, it would still be an even degree. Now this one's tricky because like you don't know what, I didn't give you the factored form, right? We don't know if it's x plus 2 cubed. We don't know if it's x plus 2 to the 5th. We don't know if it's x squared or x to the 4th. But we at least know that there is some even multiplicity there for x. Okay? So you got to keep your eyes open for even multiplicities. If you find a 0 that happens twice, you have to make sure when you graph it that it touches the x-axis and turns around. Otherwise, your n behavior or your y-intercept, those things won't match.
So the zeros are the stuff on the outside of the like equation, like that x squared on there. That would be the 0.
Well, the zeros, remember back from section 4.4, we're going to do an example here in just a minute to review. If you had factored, if you were given this as your factored form, you have a 0 at x equals 0, x plus 2 equals 0, and x minus 1 equals 0. So you have 3 different zeros. It's just that your different zeros appear more often. Okay. So anything that crosses the axis that's odd multiplicity, we usually don't talk about odd multiplicity because the most common odd multiplicity is 1, and that's uninteresting when a 0 happens once. Okay, it's a 0. Okay. But 2, 3, 4, those are going to be more interesting multiplicities we'll need to name.
So the one that is third spot on the x-axis where the line crosses and just be straight up, is that another odd multiplicity?
That, yeah. X minus 1 has odd multiplicity. It has multiplicity of 1. So it crosses the x-axis. Which, when a 0 appears once, that's just what it does. Okay, so we're going to see this kind of play out in some of our graphs today. Let's look at an example together and kind of put section 4.4 together with this graphing and multiplicity piece. Okay. So on your homework tonight, make sure that you read the directions. Do whatever your direction is asking. If it's asking you to find the zeros, if it's asking you to graph, we've got f of x equals x to the 4th minus 3x squared, or sorry, minus 3x cubed minus 4x squared. Okay, I'm going to start with that first direction. Find the zeros of the function. So far, what's our basically singular method for finding zeros of polynomials? Factoring. So we're thinking about our pink sheet, our little diagram there. I might check for a greatest common factor. Do these 3 terms share anything in common? An x squared, so I'm going to go ahead and take that out. That leaves me with x squared minus 3x minus 4. Then I got to check what I factored out my GCF from. Does that also factor? That's a trinomial. Do you have factors of -4 that add to make -3? -4 and 1. So you have x minus 4 and x plus 1. Okay. Okay. And then we're going to set our factors equal to 0 and find out what our zeros are, right? So x squared equals 0. We would square root to solve, and we would just get x equals 0. Normally with a square root, what do? Plus or minus, but I'm not going to put that there because we would argue 0 is not positive or negative, so we don't really put plus or minus in front of 0. But we would say after our previous discussion, that's 0 with a multiplicity of 2, right? There's actually 2 factors in x squared. X squared is x times x. So if I set those singular factors equal to 0, then there are 2 solutions. So I'm going to say 0 with multiplicity of 2. if it was, let's say I had a greatest common factor and I could take out x to the fourth, how many times would 0 have been a solution? 4 times. X to the fourth would be x times x times x times x. Yeah, that's how many times it's a solution. Okay, and what are my other two zeros? Positive 4 and negative 1. Didn't mean to cross that out, sorry. Okay, so I've got those zeros. How many total zeros do I have? 4. And looking at the polynomial, how many total zeros should I have? 4, because that's the degree, right? When 0 has multiplicity of 2, that counts twice. 1, 2, 3, 4. It showed up 2 times. Okay?
Where'd you get x equals 0 with the multiplicity?
X squared is x times x. That's 2 factors of x. So there's 2 zeros of 0. If it was x to the fourth, how many times would 0 be a solution? 4 times, because that's x times x times x times x. Okay, so with x to the whatever exponent, its exponent is how many times it shows up. Okay, what are those zeros going to look like on our graph? X-intercepts. Awesome. Let's draw a quick graph. Let's see, I've got 0, I've got negative 1, and I've got 4. So we're going to let our zeros, when graphing, replace our table of values. Remember when you used to plug in x and get different values of y? Now I'm just going to say use the zeros in their place. But there's one other point that's really easy to find. What will I usually have you also graph? Y-intercept. In this case, what is our y-intercept? 0, so that's not super helpful. So now the big question is, if all my points are on the x-axis, how will I figure out what my graph looks like? Use my end behaviors. So let's look at this polynomial. To determine end behaviors, we're going to look at that first term. What's your leading coefficient? Positive 1. So as x approaches infinity, what's your y doing? Going to infinity. If you have a positive leading coefficient, your right side rises. And then what do you look at to determine your left side? Your degree. You ask yourself, is your degree even or odd? In this case, it's even. So as x approaches negative infinity, what's the left side do? Also positive infinity, right? Does the same thing. So y approaches infinity. And there's one other thing I know. My multiplicity of 2, we just had a discussion. What's going to happen at 0? It's going to bounce at 0. So there's 2 ways it could do that bounce. It could bounce above or it could bounce below. That really depends on what my end behaviors are. If my ends have to rise, I've got to be going up over here. So I must come down, bounce, rise. You got to let your brain fill in the missing parts.
What if you went like down and then up, back to the point and then up again?
You crossed here?
The other way around.
Over here?
I went starting from the right side. I went starting at that point. I went down, then up, no up again. Keep going up, up.
You're going to come draw it. I don't understand what you're saying. Or show me your paper. Okay, does anybody else have any other questions? Let me see what you got. No, you have an extra 0 that we didn't find. No good.
Are these all going to kind of like look like weird W's?
They're gonna have curves. I'm going to draw Lexi's. Actually, I'll draw Lexi's on here. Okay, here's what Lexi's look like. I'm glad you did this, Lexi. This is good because this happens a lot. Some people did it on their concept check. Did you start from the right side? Okay, so she started from the right side and she went like this, and she went like this, and she went like this, and then she just needed to go back up, right? But this is going to be wrong because somewhere out there she has a 0 that we didn't identify. So you can't have an extra x-intercept that isn't really there. That's why you solved for the zeros, right? Okay, so I'm really glad you did that. Thank you. Okay, we could show that. And notice she doesn't have even multiplicity right there.
There's.
Okay, so you've got to have the matching image of even multiplicity. Okay. Now, the next part of our notes is going to be the rational root theorem. I'm going to give you a piece of paper. You are not required to put this in your notebook, but if you wish to, you have some scissors and some glues at your pods. So if you would like to cut it down to size so it fits in your notebook, if you would like to glue it in, there's a blank back side, you can fold it.
Wait, so how would we fold this thing?
I'll give you just a little bit of time to try out the fold and see what works.
Glue down.
Stuff from yesterday?
That, right there. Okay, make it chill out, okay? Calm your attitude. You're out like a 10 right now, and you feel like
Okay, so if you need a minute, take a quick moment if you're going to put it in your notebook. Do it quickly.
Thank you.
There's one on the floor.
Yeah,
You can pick them up now. Save me some time
Avery's
later.
kicking it.
Where did you get it?
Kenzie was stealing it. I got it.
Okay, there's a lot of information being thrown at you today, so you gotta be like alert and awake and paying attention. I'll be with it. How about
Oh, that pisses me off. Look how close it is.
put it this way?
No, that's just, look how annoying that is. It's just like, just off the edge of the page. Well, if I cut it, it's gonna cut the graph.
I tried cutting it. There's a top
Shout out TJ. You didn't even do your daily spin. You're right. They made a whole new place for it, too. It's better than it was.
Okay. So if you don't like to put stuff in your notebook, you don't have to. If you want to, you can paste it in or whatever works for you. We're going to talk about our next topic, which is the rational root theorem. We're going to do some graphing. Woo! Yes. It's good stuff. And we'll be practicing this skill multiple days. Okay, so you don't always have to get it on the first day, but you got to try it on the first day. Okay. So the next part of section 4.5 comes from this issue. Of course, I've always given you polynomials that factor because we were working in 4.4 and I wanted you to be able to solve by factoring. And then that was the only method we had to solve, so I made the last polynomial something that you could factor. But what if there's a polynomial that you can't factor?
Then we're screwed.
Yeah, up until this point, you don't have another way to find all the zeros, right? So I'm going to answer that question. We're going to use something called the rational root theorem. And now is a great time for me to talk about the word root. So root of a polynomial is just another word for a zero. So sometimes this is also referred to as the rational zero theorem. And a zero can also be called an x-intercept as long as it's real. We just talked about that previously. And there's a fourth word that we use for these. Solution. So there's my abbreviation of solution again. So zeros, x-intercepts, as long as they're real, solution, roots, those things all mean the same thing. So if there was a question ever that said, what are the roots of the polynomial, it means solve the polynomial. Emily. Oh, okay, yeah, I got an extra one. I'm imagining you may not be long. All right, and we're going to use the rational root theorem to make a list of possible, rational, oops, can't talk and write at the same time, possible, rational zeros. Okay, what does it mean when something is possible?
It's going to be on the graph.
It can happen, but it won't always happen. So this is a list of zeros, like these things could be zeros, but this is not the list of zeros. Okay? What does rational mean in mathematics? What's that? Well, rational in context of anything in the real world might mean fair, but in math, what do we mean when we say rational numbers? It's a number that can be written as a fraction. Now, you could also sometimes write it as a decimal as long as it terminates or repeats, right? Okay, but I would argue it's just like some number that we could write as a fraction. So this means if we're making a list of things that could be zeros that are rational, there are some things that are not on the list. Do you agree with that? Like there are no imaginary solutions on the list. There are no irrational solutions on the list. So just kind of be aware of that. Okay, and why do we do this? Okay. So I'm going to argue if you can't factor a polynomial, the other way you could solve will be to divide the polynomial by linear factors until you get a zero remainder. And if you don't have the rational root theorem, you're starting from negative infinity to positive infinity. You could check anything.
That's a lot of infinity.
That's a lot of numbers. So the rational root theorem will narrow down the list. Now you'll see in our notes today, maybe sometimes that list is still awful long. But it's better than negative infinity to infinity. Okay? It gives me a place to start checking. Okay, so down at the bottom of this paper, it says, if a polynomial has rational roots, and I'm going to put fraction there just as a reminder, then it will come in the form plus or minus, and then we're going to call them P over Q. This is a new P and Q, different than the P and Q we used back in quadratics for intercept form. And we're going to label P is factors of the constant. Where do you find the constant in a polynomial in standard form? Way at the end. Over Q, factors of the leading coefficient. Where's the leading coefficient? Way at the front. So you're doing the factors of the two numbers on the bookends of your polynomial. And we're going to do this for this example. So we're going to do some plus or minus P over Q's. Now, because of the plus or minus, you don't have to worry about what the sign of the leading coefficient or the sign of the constant is. You just like look at the number. Okay. So what's our constant? Our constant is negative 12, and I don't really have to worry about the negative 12. I'm just going to say 12. What are constants of 12, or what are factors of 12?
6 and 2.
1, 2, 3, 4, 6, and 12. Now, you don't have to write them in order, but I like my numbers to be in order. So I have to write them in order. Okay, for me those are all my P's. My Q's are factors of the leading coefficient. What's the leading coefficient? 3. What are factors of 3? 1 and 3. Okay, so to make the list of possible rational zeros, we're going to make the list of plus or minus P over Q. I'm going to do more work than I usually do right here. I'm going to take all the P's. 1, 2, 3, 4, 6, and 12. I'm going to put them over all the Q's. 1 and 3. Okay. Now, you want to give me your final answer in simplified form. So, like, take all of those numbers, 1, 2, 3, 4, 6, and 12, and divide them by 1. What happens to each one of them? They stay the same. So my actual list of possible rational zeros starts with 1, 2, 3, 4, 6, 12. I'm doing 1 over 1, 2 over 1, 3 over 1, 4 over 1, 6 over 1, 12 over 1. They are what they are. And then I'm going to do them all over 3. Now, you do not have to write down any repeating solutions. So if it reduces to be something already on the list, don't write it again. Okay, only write the new ones. 1 over 3. Is that on my list? No. 2 over 3. Is that on my list? No. 3 over 3. Already on the list as 1. Okay. 4 over 3. Nope. And then 6 over 3 and 12 over 3. Already on the list. So that's my full list of possible rational zeros. They can't all work because that polynomial has a degree of 3. But if there are some zeros that can be written as fractions, it's one of those numbers. So now I don't have to check from negative infinity to infinity. I just got to check this list. What's that? Yeah, it's on my list. My options are plus or minus 1, 2, 3, 4, 6, 12, 1/3, 2/3, 4/3. How many options are there?
No, there's more than 9.
18. There's 9 positive and 9 negative. So I will give you a break on plus or minus. You can just write plus or minus at the very front. You don't have to do it for every single one, but understand that the plus or minus applies to the whole list. Okay, now, it is never my goal on a problem for you to check all 18. I would hope that you will find one before you got that far. And I always tell my students, like, start at the beginning of those, like 1, 2, 3, and hopefully you'll find one before too long. All right, so let's open up that sheet. We may only get through one example, so you gotta make sure you're paying attention and you're asking good questions if you have them. Okay, because then you'll have this one example to help you with your homework tonight. I'm going to give you some time. Why don't you fill out A through G on your own? You don't have to do all of this for your homework tonight. However, it's a good time to review all that stuff we did early in the chapter. Talk to your group if there's any that you forgot how to do. I'll be calling on you for your answers here in a minute. Oh, and for D, it says total solutions. What's another word for solutions? Zeros, the total zeros. I could use those interchangeably. That's a great reminder for me. You can put those in here. Blue sticks. It's okay, you were in Theorem before. No, put those back. Okay. Let's see. Sarah, what'd you say for type? Quartic. Awesome. Elvis, what do you say for degree? 4. Excellent. Mickey, what do you say for leading coefficient? 2. Awesome. Kristen, what do you say for total solutions? 4. Remember, that's the same thing as total zeros. Sierra, what do you say for max turns? Sierra up here. 3. 1 less than the degree. Awesome. Megan, what do you say for y-intercept? -30. And I'm going to write mine as the ordered pair, 0, -30. Okay, and then for end behavior, I've got my right and left statements up there. As x approaches infinity is to the right. As x approaches -infinity is to the left. So I'm going to need to describe both arms. Okay, so for the right side, as x approaches positive infinity, what am I going to look at? The leading coefficient, which we said was 2. And so because it's a positive 2, what's my right arm doing? Rising, so I will say y is approaching what value? Positive infinity. I'm reaching towards positive infinity. To determine my left hand behavior, look at the degree. The degree is 4, even. So what should my left side be doing? Also approaching positive infinity, right? Okay, got both my hands up. Okay, so now I know what the ends of my graph are going to look like, right? Arms up in the air. Okay. All right, now we're going to do some new stuff. Instead of making the listed table of values, let's solve for our zeros. Because this one can't be factored. We've never talked about factoring with 5 terms. We're going to make a list of possible zeros and do synthetic guess and check. Okay, so for my list of positive zeros, I want my plus or minus p over q's. What's p? That -30. What are factors of -30? 1, 2, 3, 5 and 6, 10, 15, and 30. Okay. Yeah, that is a lot, isn't it? What's my leading coefficient? 2. That's where we get my q's. What are factors of 2? 1 and 2. Okay. So with your q, there's always going to be a 1 there, right? So you're always going to have the list of those numbers that are p, just like as they are. So if I take all those numbers for factors of 30 and put them over 1, they're just themselves. So for my list of possible rational zeros, I'm going to say plus or minus 1, 2, 3, 5, 6, 10, 15, 30. And then I'm going to go back and I'm going to put all those numbers over 2. What are the only types of factors that are going to produce a new solution or new number?
1, 5, 15.
What kinds of numbers are those? What kinds of values of p will give us new zeros? The odd ones, right? Like 2 over 2 is going to be 1. 6 over 2 is going to be 3. Those things are already on the list. So I'm just going to go through and pull my odds. So I'm going to have 1 half, 3 half, 5 halves, and 15 halves. Whew. How many numbers are on that list?
1, 2, 3, 4, 5, 6, 7, 8, 9.
I think it's 12. Yeah, so 24. There's 24 numbers to check. But hey, isn't that better than infinitely many? Now, let's crowdsource. I'm going to have this group check 1. I'm going to have this group check -1. Have you guys do 2. You guys do -2, 3, and -3. So we're going to check them in synthetic, and what do we want to be true?
No remainder.
No remainders. So set up your synthetic. Okay, so we're going to set up synthetic. I'm going to call this synthetic guess and check. You're just checking these numbers until you find one that works. We're looking for a smiley face. But we're checking the numbers from the list, not just any old random numbers. Did any groups find one that worked? One works. Okay, so I'm going to work out one. If you worked out any others that work, just leave your work, or you can build off of that. I'm going to build off of one here in a minute. So one works, so 2, -6, -6, -26, -26, and then I get 30, which, yay, I'm so excited. I know it's going to work. Now, this was an x to the fourth polynomial, right? So this one is now x cubed down here. Now, I can factor a cubic polynomial with 4 terms by grouping. However, I can tell from the numbers down there, like that doesn't group. When I factor out like 2 out of 2 and -6, I'll be left with like an x minus 3. And when I take out, what did 26 and 30 have? A 2, I'll be left with 13 and 15, so that's not going to match. So it doesn't factor by grouping. So that means it's like our box problem with our volume. If you find one that works, keep going. So did anybody else's number work? Are you sure? Who's my 3s? What about -3? I think -3 works.
-3s.
It does. -3 works. I think.
We didn't have none.
Oh yeah, -3 works. Okay. So that means if I divided it again, since I was at an x cubed, now I'm at an x squared. This is x and this is a number. And every time I get to a quadratic, I could solve every quadratic. I can either solve by factoring. I can solve by taking square roots if there's only one x squared in the whole equation. Or I can do quadratic formula. So never will I ever not be able to solve. You can come in and sit in the back. So I'm going to write this out as a quadratic, 2x squared minus 12x plus 10. Set it equal to 0. And what would you probably attempt for solving here? Factoring. What do you notice all 3 terms have? A factor of 2, so I'm going to take out a GCF. That's 2 times x squared minus 6x plus 5. You have factors of 5 that add to make -6. -1 and -5. And then you don't really have to worry about the 2. That's not going to produce a solution. What are your 2 solutions from this factoring? 1 and 5. Side note, if you're solving a system, please do that on 24. Okay, good. Thank you. Okay. So 1 and 5. And what were the other two zeros that we had from synthetic guess and check? 1 and -3. So 1 happened how many times? Twice. It has even multiplicity. So I'm going to list my zeros. 1 with multiplicity 2. And -3 and 5 are my zeros. How did I know it had a multiplicity of 2? It showed up 2 times. Once in synthetic and once in my factoring. Where am I going to plot those points? As x-intercepts. So -3, +1, and +5. What's the other point I like to plot? My y-intercept. Now, this is a good one because it always bothers my students when -30 doesn't fit on the graph, right? This is my solution. I don't want to run into my writing. I'm just going to call this 0, -30. If it's going off the graph, just drop it and label it. I get it. Okay, don't worry. Scaled out, especially if it's -30 and it's like in your other problem. Okay, I don't need you to do that. I get it. Okay. And then the last thing is pay attention to your end behavior. My both arms are rising, and pay attention to your multiplicity. At which 0 do we have to be really careful? 1. That's this one right here. So if this side is rising, that means I must come down, come up, turn, come up. Oh yeah, thanks. I missed my y-intercept. Thanks. How about that? Good catch. Okay, now on your homework tonight, you do not necessarily have to write all this out. This is just good review for us. But you should be thinking about end behaviors and y-intercepts, max number of turns, and max number of zeros. And be careful, don't do that thing where you add a 0 that we didn't find. You guys did awesome. That's a lot of information, I know.